Hi everyone, this is Mr. Blitzstein. I hope you're doing well in this very, very odd time. And I realize that doing schoolwork has probably been far from your brain at this point. You've been stuck at home and little to do and much desire to be with others. But I hope you're being safe and being smart. And we're going to slowly ease back into things with videos such as this. So screencasts and videos and links to YouTube and various other avenues to make sure that you kind of ease back into the process, but get that brain working. For those who aren't a student of mine, obviously you're going to watch this video courtesy of me. But as far as the end, if you have questions, you're welcome to address them to me or your actual math teachers. Likewise, student of mine, you're welcome to address questions to me or again other math teachers if you so desire. But we're going to do the best that we can. At this point, if you haven't already taken out maybe a paper and pencil, that would be smart. Likewise, if this is too fast or too slow for you, you do have the luxury, again, being this is a video, to slide forward or pause and come back, or pause and review, or really you dictate the speed at which you work. So keep that in mind, and just know that later on I'm going to tell you that if I'm going to leave a problem for you and then give you some time to solve, I make a little noise so that you know, like, wait, I didn't get there. Let me pause it so I don't see what the actual answer process is without trying on your own first. All right, so with that in mind, if you do need to go ahead and pause it now to grab a pencil and paper, that might be smart. Calculator is always helpful, again, if you'd like, either online or your own. Likewise, there was a handout, and if you haven't already printed that out and you want to go do that now, go ahead. Likewise, you can just take a picture of it, or you can do whatever it is that you feel is appropriate so that you have that handy. Lastly, being as how you haven't seen me in a while, maybe you haven't had me at all because you're not a student of mine, that you should at least know what I look like. So mind you, we've been apart for quite some time with this whole social distancing thing. I haven't been as prim and proper as I normally am, but just so you know, this is the image you should associate with my voice. All right, let's get going. So we're going to all about simplifying radicals today, and we're going to learn two methods, and hopefully this is more of a refresher than learning, but either way, we are going to look at two methods. The first method is going to be using perfect squares. That's the method I have taught you if you're a student of mine. That's the method I'm going to lean towards as we go through this video. That said, I am going to show you two methods, the other one being the use of a factor tree. Excuse me. And again, I will show you both these methods for our opening 3 practice problems. Thereafter, I'm just going to be doing the perfect square model. Now, know yourself. If in following those 3 or just in your past, you prefer this model, that's fine. The answer should be the same, just the steps in between will be different. Alrighty? So with that in mind, let's jog our memory on what perfect squares are. So this is the handout that you may have already printed out or received or looked at, or I don't know what, but that was the handout I referenced before. These are numbers you're going to want to learn, memorize, maybe already know. And again, if taking a picture does the job for you, that's fine, but these are the numbers we're going to play with when we use the perfect square model, our 1, 4, 9, 16, 25, and so on. You want to learn them, memorize them, know how to use them. And quite honestly, it would be great if you knew more than past the first 12. Again, they're pretty much just these numbers squared, right? So you can see a 1 squared is a 1, 4 squared, 16, and so on. And the connection is that, right, the square root of this number, the square root of the perfect square, gets you these nice, neat whole number square roots. That's kind of why they're called perfect squares. Okay. So let's go ahead and try our first practice problem. And like I said before, we're going to do 3 practice problems using both methods. So again, we'll get the same answers. Just how we get there will be a little different. Thereafter, I'm just going to model or work through the perfect square method. So our first practice problem is simplifying the square root of 45. So the whole perfect square method is basically you want to find the biggest perfect square that divides evenly into 45. Okay, so hopefully you have that list handy. It's in your brain, or if you want to pause it now and go back, that might be smart, but that's the idea. Find the biggest perfect square that divides into 45 evenly. And the biggest perfect square that does that is 9. And 9 goes into 45 5 times. We write that as root 9 and root 5. Sorry, square root 9 and square root 5. Okay, these are not random numbers. We try to find a perfect square that goes into 45. And 9 is indeed a perfect square, and it's the biggest one that goes into 45 evenly. Then your next thought is, well, you picked this for a reason. And that is the square root of 9 is a nice, neat whole number. It's 3. So this is going to become a plain old 3, and we leave the square root 5 all alone. And there you go. That's how it works. Okay, let's check out the same problem, but using the factor tree method. So I'm going to cheat a little bit. We're going to do this twice, but the idea is you're just going to break the number down to its factors. So we already saw that 9 times 5 gets you 45, and hopefully you knew that anyways. But factor tree method is you break down the factors, but you just keep on going until you end with a prime number. So both 9 and 5 go into 45. 5 is prime, right? The only way to multiply to get 5 is 5 and 1, so there's really nothing to do here. But 9 is not prime. It can be broken down to further factors, such as 3 and 3. Now, 3 and 3 cannot be broken down any further. They are prime, so you have fully factored that particular problem as far as the factor tree is concerned. That said, being that we're not necessarily using perfect squares, it's not only just 9 and 5 multiply get 45. There are other factors. So let's just say you thought about 15 and 3, because 15 times 3 is 45. Same process still applies. I can't break down 3 anymore because that's prime. But 15 definitely has factors, and those are 5 and 3. And again, those are prime numbers. So even though we may have started initially the same way, what you have left over from each one of these branches in your tree is a 3, 3, and a 5, right? A 3, 3, and a 5. They still have 2 3s and a 5. So start off differently, but ended exactly the same. Thereafter, you are looking for having the same number twice, or pairs of the same number. And the idea is square roots and squaring are kind of opposite and deal with the same thing times itself. So again, two numbers that are the same. Same thinking here. So here again, we saw we had 2 3s. Here we saw 2 3s. For every pair that's the same, that one number is going to pop outside of the root. And whatever's left over, so in this case, the 5s, will stay inside the root, leaving you with an answer of 3 root 5. Again, it's the same problem, so it should be the same answer as the other method, just a matter of how we get there. Let me repeat again where that 3 came from. Again, the idea is once you get down to your prime factors, anytime you see the same factor twice, that number will pop out just once. And whatever was left over, the 5, that go ahead and stays in the root. Let's try another using both methods. All right, so we got the perfect square method to try to break down 108. So again, the thinking here is trying to find the biggest perfect square that goes into 108. So I hope you have that list handy, or you're going back to it, or you're looking at your picture, whatever it is that you need. But see if you can find the biggest perfect square that goes in 108 evenly. And I will make a sound when I'm about to move the shade. So if that was too fast for you, just pause and keep working. Okay, hopefully you found the biggest perfect square that goes to 108 was 36. And 36 goes to 108 3 times. Again, these are not random numbers. It was try to find the biggest perfect square that went in 108, and 36 was the biggest perfect square that went in 108. That said, hopefully you recognize this number. The square root of 36 is a nice, neat 6. That's why we used it. So a 6 pops out, and the root 3 just stays as it is. Sorry, the square root 3 just stays as it is. All right, so let's say I'm gonna do the same method again this time before I do factor tree. Let's just say you did what you thought was correct, as in you used your perfect squares, but you didn't go as big as 36. It's not wrong. It's just gonna cause more work for you. Let's just say you thought, well, 4 is a perfect square, and that goes to 108 evenly. I'm gonna use that. That's great. It's correct, and you're gonna think, oh, good, I'm done, because you took the perfect square out and you got your nice neat 2. The only problem is you can break down 27 more, which is to say there's a perfect square that goes into 27. And that is 9, right? 9 times 3 is 27, and the square root of 9 is a nice, neat whole number. What is the square root of 9? Now it's righty, it's 3. So that would play out as such. Again, the 2 times the 3 will get you your 6 root 3. Again, it's the same answer, but undeniably more steps. Okay, let's try it the factor tree way. So again, I don't know about you, but I don't naturally know numbers that go into 108. Granted, we just saw some things, but if I was honestly doing this problem, having not already done a different method, I would be like, you know what? It's even. Let me just start with 2. If you went bigger, great, but that's what my brain naturally would have done. That said, I can't break down 2 anymore. 2 is prime, but I know I can break that down some more. So I know that 9 and 6 get me 54. Now, again, the question is, are these prime? Can I break down 9 further? Yes, you hopefully can. Same thing with 6. Neither one of those are prime, so we keep breaking them down. Now, at this point, these are all prime numbers. They cannot be factored any further. So we've done our factor tree all the way through, and now we're concerned with these numbers. This 2, this 3, this 3, this 3, and this 2. If you remember from before, we're looking for, ideally, pairs of the same number. So do you see any pairs? I would imagine you do. Hope you saw 2 pairs. There were 2 pairs. There's 1 pair of 2s and 1 pair of 3s. Now there are 3 3s, but again, we're looking at pairs, right? Squared and square rootings imply something times itself, just twice, not more than that. So again, we have a pair of 3s and a pair of 2s. So for each one of those pairs, we're going to pull out that number. So we're going to pull out 1 2, and we're going to pull out 1 3, and then I'm just going to leave this 3 inside the square root symbol. Again, so we pulled out that 1 2, pulled that 1 3, multiply them together to get the 6 on the outside, and this remaining 3, whoop, went back inside the square root sign. Again, it's the same answer because it's the same problem. It's just a different approach. Okay, we're going to try a third practice problem also using both methods, but thereafter, I'm just going to kind of talk through, show the perfect square model. Alrighty, so trying to find the biggest perfect square that goes into 48. Go ahead and see if you can scan your list. Find the biggest perfect square that goes into 48. When you hear that sound, know I'm about to move the shade. If that was too fast, just go ahead and pause and keep working. Alrighty, hopefully you found your biggest perfect square to be 16. Yep, 16 times 3 gets you 48, and 16 is definitely a perfect square. Square root of 16 is a nice, neat 4, and then and square root 3 just stays inside. As far as factor tree method, I'm not sure what you thought the factors of 48 were, but I went with 8 times 6 as the first factors that I thought of. Again, neither one of those are prime, so I have to keep going. 3 and 2 are both prime, so I know I'm done with this part. 4 and 2, 2 is prime, but 4 is not. It can be broken down some more. So I'm breaking down 4 some more. We end up with 2s. So again, now all the numbers that are left over, these are all prime, so we're going to work with those. And again, we're looking for pairs of the same number. Hope you saw 2 pairs of 2s, right? You got the red 2s and the purple 2s. And again, looks like 3 is the odd number out in this situation. So again, we got a pair of 2s and another pair of 2s. So we should pull one of the red 2s out and one of the purple 2s out, and then leave 3 as inside the square root. And there you go. Again, the idea is this 4, again, came from one of these 2s times one of these 2s. Right? Because for every pair, you just pull one of those out. All right, so we've done 3 practice problems with both methods. The rest of these problems will be done using the perfect square method. That said, if that's not your taste, feel free to keep doing the factor tree method way. Just know you'll only have an answer to check, not the steps in between. All right, practice problem 4. Let's see what you can do. Try to find the biggest perfect square that goes into 72 evenly. Again, the sound will dictate when I'm going to move the slides, or the shade, excuse me. So if that was too fast, just pause it and keep working. Hopefully you found that 36 was the biggest perfect square that goes into 72, and it goes into it evenly twice. Thereafter, again, square root of 36 is a nice, neat 6, and then square root 2 just stays as it is. If you hadn't thought about using 36 and you use 9, again, it's correct. It's just going to cause you more work. So again, you're looking for the biggest perfect square you can find. If you did use 9 and 8, it will still play out and get you the correct answer. It's just more steps. All right, let's try a fifth practice problem. There's that 3 in the front. That's weird. All right, well, let's not freak out. Let's just essentially temporarily ignore it. It's there. Keep it there. But just play with the root 80. See if you can find, again, the biggest perfect square that goes into the square root, goes into 80 evenly. All right, so leaving the 3 alone temporarily, I was able to find that 16 is the biggest perfect square that divides into 80 evenly. Again, the last time I checked, the square root of 16 is a nice, neat 4. So we're going to multiply these values and leave the square root of 5 all alone, leaving us with, you got it, 12 square root 5. All right, practice problem 6. Let's do it. Same idea this time. There'll be a number in the front. But you can do it the same way. Let's see what you can do. Trying to find the biggest perfect square that goes into 60 evenly. Again, ignoring the 5 temporarily. Biggest perfect square that went into 60 was actually a fairly small one. It was 4. Again, 4 times 15 gets you 60, and 4 is indeed a perfect square. Square root of 4 is a nice, neat 2, so that'll come right out of the root. And last time I checked, 5 times 2 is, you got it, 10. The answer is 10, and the root 15 just stays as it is. All right, we're going to try one more. That's what you're used to. And then we're going to close out with 4 other ones that are a little bit of a stretch for you, maybe even new for some of you, whether you're my student or not. Still going to be radicals and simplifying them, just a slightly different process. Either or, let's try one more like we've been doing, and then we'll change it up a little bit. Let's see what you can do. I'm not going to say a thing. You just try it out. So, how'd you do? Not too shabby. Hope you kicked some butt there. And if you did, or if you gave me some honest effort, all I can say to you is, good job. Alrighty. Practice problem number 8. So again, we're going to do 8, 9, 10, 11. So we're going to have about 4 more. They're going to be slightly different than what you're used to, but they're still radicals and essentially still following a lot of the same rules we've already learned. That said, let's see what we can do. Alrighty, so we have seen the number outside of the square root sign, but we have not seen the whole quantity being squared. All right, well, let's just think about what that actually means. Squared just means times itself. So really all this boils down to is 2 square root 5 times 2 square root 5. All right, that's not too crazy. All right, let's just go ahead and multiply our part. So 2 times 2 will get us a 4. And square root 5 times square root 5 is just square root 25. Now, I don't know about you, but as I said that, I'm thinking square root of 25. I feel like I know that. And hopefully you do between what you've been looking at today and just general knowledge, right? That is a perfect square. As in, what is the square root of 25? That's right. Nice, neat 5. Absolutely. Leaving you with dun, 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 20. Now, I'll be honest with you, I'm going to do this same problem a slightly different, I think, a little faster way, because the thinking here is square roots and squaring are just opposites of one another. Just like adding 5 and subtracting 5, or times 3 divided by 3, they offset one another. Same thing with the square root and the squaring. So much if you noticed, but we eventually just had 5 outside the root down here, and this 4 came from somewhere. Let's think about that for a second. Let's take the same problem and look at it a little bit differently. Again, the idea is squared is these things are being multiplied themselves. It also means each individual part is being squared. So let's think of it as being that. Right? This part being squared, and this part being squared. Again, 2 squared is just a straight up 4. Again, the idea is a square root squared will just kind of offset itself, and the number will just pop right out. You could think of it as, hey, becomes square root of 25. The square root of 25 is just 5. So I'd like to see if you can learn that, again, a square root being squared, they offset, and the number just kind of pops right out. That's it. Again, it's the same answer because it's the same problem. It's just a slightly faster, maybe less work approach. All right, let's try another problem just like one you saw. I want you to try without me first, and we'll see how it goes. All right, so I'm going to go with that second approach as far as I'm going to square each individual part. So I'm going to square the 3 and the square of the root 20. And the thinking here is, again, a square root and a squaring are going to offset one another. So this number should just pop out. And 3 squared, I'm pretty sure I can handle. Yep, right. 3 squared is the 9. Again, a square root, when it's squared, just cancels right out. Or offsets one another, I should say. And last time I checked, 9 times 20, 180. And our last two are also a slight variety of what you've been doing. They still involve roots and some of the roots rules, but different kinds. So let's focus in on these last two, and then we'll call it a day as far as the instruction piece. Alrighty, so we got a fraction, which is everybody's favorite. And then even more importantly, what you have to notice here is there is a radical or a root in the denominator. So there's kind of an unwritten math rule that we do not leave radicals in the denominator. So how do we get rid of it is the question. Well, like what you just saw, if we could do a radical or a square root times itself, it seemed like the number just kind of popped right out and the root just disappeared. So we're going to try that. We're essentially going to say, hey, if I can do a root 3 times a root 3, a 3 will just come out. This is how we look at that. Now, I just hinted at doing a root 3 times a root 3 down here. Well, the idea is whatever you do to your denominator, you're going to have to do to your numerator as well, which might seem a little crazy, but if you think about it, right, what is the same number over the same number? That's just a 1, whether it's 8 over 8, 2,000 over 2,000. Same thing over the same thing is the same as just 1. If you multiply a number by 1, it doesn't get bigger or smaller. It doesn't really change at all. It'll change the way it looks in this context, but the value is not changing at all. So we are indeed allowed to do that. All right, so we already saw that a root times itself would just cancel out, but I went a little further here and actually showed you the steps, and then a root 3 times a root 3 is a root 9, which we'll clean up momentarily. As far as the numerators, you can just kind of smush them together. That's outside the root, that's inside the root. You cannot actually multiply them, so you just put them together. That said, I believe you know root 9. It's a nice, neat, perfect square. So it becomes just a plain old 3. Now, sometimes that's all you do. Sometimes there's more to do. And when I say more to do is what you have to consider is, could you have done anything with this 10 and 3 as, and could those be reduced? Well, there is no value that goes into both 3 and 10. So leave it the way it is. If there was, though, you would have to reduce these. Again, you can't touch the radical, but if there was a way to reduce these two values, you would have to do that. Let's try another one that's more or less just like that. Of course, if that was too fast, feel free to pause, take a minute, rewind, rehear me speak, whatever it is you need. It's not a race. You control the speed of this. But that said, we're going to do one more that was more or less just like this one, and that will be our last one. All right, so same deal here. We have a radical or a root in the denominator, and that's just not okay. We got to get rid of it. And the way you get rid of a root is you multiply both in the top and the bottom by that root, or by that radical. So that would be our first step. Both the numerator and denominator times a root 6. Again, a root 6 times a root 6 is technically root 36, but the whole point is a root times itself, or a square root times itself, pretty much just offsets and just pops right out. Now, in the previous problem, that was all we did, but in this case, we do have to at least look at these numbers and see, hey, can these be reduced? And hopefully you can see that they definitely can. 6 goes into both of them, right? So 6 goes into itself once, 6 goes into 12 twice. So you are left with 2 root 6. Alrighty, so again, we went through that as smoothly as we could, but does not mean you feel great about it. So maybe look back at your notes, whatever you wrote down or tried to do. Maybe go watch it again and tweak a thing or two. Likewise, feel free to reach out to me, or if you're not a student of mine, to reach out to your math teacher for any questions or concerns you have. Likewise, if you're a student of mine, you want to ask someone else questions, that's more than kosher as well. You do whatever you got to do to make sure that you're okay. Ideally, I'd hope you feel comfortable reaching out to me first, but I understand if that's not your style. All right, so that was the practice. You're going to get some, so that was the instruction, excuse me. You will get some practice opportunities as well. And yes, feel free to reference this video again, whatever notes you took, and things of that nature. Hope that was not too painful for you. Hope you are okay. Feeling like this is more of a refresher than something brand new, except for maybe those last 3 or 4. Either way, give yourself a fair chance, practice, and let's see how it goes. All right, and with a closing thought, I have a little joke for you, so I hope that makes you smile. Here is the joke. Seemed fairly appropriate in light of the Passover Easter time. And as far as the punchline, all right, folks, hope you're well. Take care of yourself, and I'll hear from you soon, I hope.